Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on December 3, 2025, about 2 days ago. It introduces double interactive reinforcement learning, which teaches vision language models to coordinate many tools and reaches state-of-the-art spatial reasoning, including gains of 12% over vanilla SFT and 16% over standard reinforcement learning on the RoboSpatial benchmark. The paper is titled SpaceTools, Tool-Augmented Spatial Reasoning via Double Interactive RL, and as we will see later, the implications for tool-driven robot control are quite significant. Figure 1 illustrates how the system uses multiple tools to answer a precise spatial question about guitar pedals. The top panels compare a simple one-shot response and a longer thinking style answer, which both describe the scene but never verify geometry. The lower strip shows a tool calling pipeline that successively runs a depth estimator, a segmentation tool, three-dimensional bounding box estimation, and finally, a pointing tool. This multi-step tool chain produces a grounded answer that both identifies the smallest pedal and pinpoints exactly where to press it. So while Figure 1 showed a single example of tool use, Table 1 summarizes how different prior systems handle tools during training. This table highlights that most methods either use tools in a fixed, hand-designed pipeline or skip reinforcement learning. A non-fixed tool pipeline means the model can choose which tools to call and in what order. Interactive tool call means the model decides about tools on the fly during training. SpaceTools is the only method that combines supervised fine-tuning, reinforcement learning, flexible tool sequencing, and fully interactive tool calls. Figure 2 explains how the model actually learns good tool use through interactive reinforcement learning. The left rollout module takes an image question, queries the toolshed, and lets the policy alternate between thinking steps and tool calls before giving an answer. The middle panel shows many such multi-step rollouts happening in parallel. The right block groups the rewards and uses group relative policy optimization, which is a reinforcement learning update rule that compares whole groups of trajectories, with KL regularization keeping the new policy close to a safe reference policy. Table 2 presents the scorecard showing how well different models handle spatial reasoning, and it makes clear that SpaceTools 3B sits at the top. Normalized accuracy here means every task's score is scaled, so that 100 represents perfect performance. The upper blocks list strong proprietary and general open source systems, which already do reasonably well. The lower blocks compare spatially specialized models and tool-free fine-tuning baselines, and SpaceTools 3B still achieves the best overall scores across RoboSpatial, RefSpatial, CV Bench, and BOPASK grasp tasks. SpaceTools shows that giving a vision language model access to many real tools, then training it with double interactive reinforcement learning, can turn fuzzy visual intuition into accurate metric spatial reasoning and real robot skills. The broader message is that smart tool orchestration can rival raw model scaling. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.